Okay. All right, everybody, let's get started. So I know that probably the first question everybody asked or was thinking is, am I going to have the exams graded today? No, they're about yay thick, so it's going to take me a while to get through them. My goal is to try and get those graded by Wednesday, so like a week after the exam. I have another exam in another class I'm giving today at 10. Bless you. So it's just going to take me a little while to get through them. A little bit on the logistics so that everybody understands. So the first thing is that I always like to share, at least for the class, like the overall class performance, and I'll do that through Teams. I'll record a short little video where I go through like the class statistics, so what was the average on the exam and how everybody did on each problem, so you can kind of get an idea on that. The other thing I'll do is, so the way that I grade the exam is everybody will get an individual email that has like your point deductions and what you got wrong and why you did it. It's a really efficient way of grading this many exams, but at the same time ensuring that you all have the feedback that you need. And then I'll make the exams available probably either in my office or at some point I might bring them here to return them to you. The other thing I'll mention in that recording is I will give you just some sort of tips and tricks for future exams. One of the things I'll tell you is that all of my exams are pretty much formatted the same way. So exam 2, exam 3, exam 4, they're going to kind of be the same format, a series of short answer questions and then a series of computational problems. And one thing I will show you, and this is something I'm going to distribute to the class near the end of the semester, but in case you were curious, I thought I'd show you now. A buddy of mine in graduate school, what he would do is, and I'm sure you all have done this before, is he would take the syllabus and then take his grades that he had earned and then try and like back calculate what he needed to get on the final to get like an A or a B or a C. He called that playing the at-home game. Right? So I've got a spreadsheet that I'm going to distribute to you all later in the semester that's called the at-home game spreadsheet. And so what it does is like you go into the spreadsheet and you put in like your attendance grade, you put in your homework grade, and all 4 exams are weighted equally so that they're all worth the same. And so like let's say this was your exam 1, exam 2, exam 3 grade. So like let's say this was your grade in the class. And so what it would do is it would figure out what you would need to get an A, a B, a C, or a D. But the point I'm making is like if you look at these 2 right here, so like for this, these are just random numbers, but like for this student, they would need this grade to get a B in the class on the final, but they would need this to get a C. So there's such a wide spread. I mean, that's a really, really wide spread. I format the exams and then the grading structure so that no one exam is really that important. So I know that some of you are like, oh, I don't think that exam went well. It's okay. I promise. It'll be okay. So I don't want you to get too worried about that. So so any questions on that before we get into the wonderful world of statics? Everybody good? Everybody get the code? Get the code? We're waiting. We're waiting. All right. Okay. So with that, let's go ahead and get into the realm of statics. First off, I hope everybody got homework 3.1 turned in. That was the homework on cross products. I've got to believe that was a simple homework assignment. I've got to believe that wasn't difficult. Just to recap, just to make sure that everybody's clear on what a cross product is. So a cross product is one of the 2 ways that we can multiply vectors. So the first unit of the class was really devoted to adding vectors. Now we need to learn how to multiply them. And there are 2 ways that you can multiply vectors. A multiplication that yields a number, a scalar, which we call a dot product, or a multiplication that yields another vector, which is what we call a cross product. And we're going to find that's much more useful in the land of statics and ultimately in the land of physics. Now, when we define that vector, we define it in such a way that we know or we have a predictable magnitude and direction. So we say that the magnitude is equal to the area formed by the parallelogram that's formed by the 2 vectors in question, and that the direction is normal to that parallelogram or normal to the plane formed by those 2 vectors. And then we went through a big old rigmarole of a derivation and found that we could actually compute the cross product of 2 vectors by forming this 3x3 matrix and taking the determinant of that matrix, that it actually works out that way. Now, the way that we compute that determinant, we sort of have two methods. We have the rule of Saris. We have the cofactor expansion rule. I'm probably going to use this one more often because I think in the end you get I, J, K. It results, while it's a little bit more writing, it's ultimately fewer steps and fewer calcs. Okay. All right. So what we're going to do now for today and for the next few weeks is we're going to discuss what I'm calling rigid bodies, but there's a theme to this concept of rigid bodies. And in order to explain that theme, I want to introduce two questions to the class, okay? So the first question, so let's take a look at these questions one by one, okay? So let's take a look at the one here on the left. So how many of you have ever played Jenga? Okay, everybody knows what I'm talking about. So if you haven't, Jenga, you have a tower of blocks that are interlaced, and then one by one, you're supposed to take a block and then place it on the top, and you keep doing that. So as you go through the game, you find that the tower gets more and more unstable, right? I think everybody's aware of that. Now, let's say that I had that Jenga table right here on this tower, and let's say that it was in a rather precarious state, okay? And let's say that the tower is right here. And I go to him and I say, I want you to take this tower, and I want you to take it, I want you to move it from here to here. All right? With just like your fingers, tips of your fingers. Now, let me ask you a question. If you were in his shoes, would you take it and move it like this? Or would you take it and move it like this? Like try and slide it from the bottom? What seems to be the most stable way of taking this Jenga tower and moving it from point A to point B? Pushing it from the top, pushing it from the bottom. From the bottom. And I think everybody in here kind of understands that from a gut instinct, right? That's simple. That's simple to understand. But why? Okay? Well, let's take a look at this from a physics perspective. Okay? So let's say I have this calculator here, and the calculator's here on the table, and I take the calculator and I push it this way. Okay? Now, this is pretty easy to push. I'm able to do this pretty easily. But if I did the same thing with the table, I've got to put a little bit more effort into it. Why? Well, the reason why is with the table's resisting, right? It is pushing back. There is a frictional force that's developed between the table and the floor. That force is greater than the force that's developed between the calculator and the table, which is why it's easier to push the calculator across the table than it is to push the table across the floor. Does that make sense? Okay. Now going back to this, so going back to the Jenga tower, so I have the Jenga tower here on the table, okay, and I push here. Let's go back to the stability issue. Why is that an issue? Well, the same thing, right? If I have a Jenga tower here on the table, right, and I push this way, the Jenga tower's contact with the table is resisting it, right? And so what you're telling me is if here's the Jenga tower, right, and I push this way and the Jenga tower is resisting, then in order to increase its stability, it makes sense to push it closer to the floor, to the table, right? So there's something to be said, there's some connection with equilibrium and how far apart these forces are from one another. Does that make sense? And so I want to dig into that a little bit, and I want to look at this example, okay? So I have here a mechanic, and I have here that this mechanic has this large wrench that he's using probably to, I'm guessing lefty-loosey. He's trying to loosen this component on this machine that he's working on. Why is he gripping the wrench at the end? Why isn't he gripping the wrench right here? Why? Putting more torque on it, right? But what does that mean? Well, what that means is, so let's go back to particle statics land, right? So in this case, I would argue that this is our particle, the actual bolt or whatever it is that the mechanic's trying to loosen. And in order to achieve the desired outcome, he's having to grip this wrench as far away as possible, okay? In fact, if this wrench was 12 feet long, that might make his job even easier, right? So there's something to be said about the relationship between what happens when forces move away from one another and this concept of rotation, okay? So like the Jenga tower, I have these two forces, right, that are acting in equal magnitude, maybe, or opposite direction, but the further apart they get from one another, the more that Jenga tower wants to rotate. I've got this particle here and this force acting laterally on the nut, and the further away that force gets away from the point in question, the more it wants to rotate. Does that make sense? That there's a relationship between the distance from the particle in question and the concept of rotation. Okay, that idea is really kind of important. Okay, and so I want to talk about the idea of translation versus the idea of rotation. Okay, Newton's first law says an object that is at rest or in motion will stay at rest or in motion until acted upon by an outside force. What does motion mean? Right? Is motion only translation? So if I have this calculator and I move it from here to here, yeah, that's motion. But is there a way of moving that calculator without translating it? Okay? For example, and to set the stage, let's look at just this simple example here on the top right. I have a beam or a rigid body that is supported by a hinge support here in the middle, and I have 20 pounds down and 20 pounds up. Now, I would argue from a sum of forces standpoint, this system is in equilibrium. There is no force acting to the left or right, and I have 20 pounds up and 20 pounds down. Boom, it's in equilibrium. Do you think this system is in equilibrium, though? No. I mean, would you want to be around that seesaw on the playground? I wouldn't. You know, 'cause that's how somebody gets hurt, right? Because while the system, is in equilibrium from a forces standpoint, that system is obviously going to want to rotate. Okay, so the idea is that when forces are non-concurrent or away from one another, we need to start to consider the possibility of rotation. Okay, I'm going to introduce to you some new definitions. Okay. And what I mean by that is, like, so for the first one, we already know what forces are. I mean, we've been dealing with forces this whole semester, but I want to reframe what a force is, or at least reframe what it might be from an engineer standpoint. I propose to you that another way of thinking about a force is any action on a body or a system that increases its tendency to translate. So in other words, a force, take a force, it wants to take the system and translate it, literally, shift it from one place to another. Whereas a moment, I'm going to propose that a moment is an action on a body that increases its tendency to rotate. Okay? What we're dealing with now are rigid bodies. What I mean by rigid bodies, I mean non-concurrent force systems. I mean, so the first module of the class, every problem that we dealt with, all dealt with situations where all the forces met at a common point. We never really needed to worry about rotation. Now we do, because now the forces are not going to meet at a common point, and so we need a formal way of addressing that. We need to understand how to ensure that the systems that we are analyzing and designing are not only not going to translate, but not going to rotate as well. And that's where the introduction of a moment comes into play. Here is the formal definition of a moment. Okay, so the formal definition of a moment is as follows. So let's say here I've got my rigid body, my potato out in space, okay? And let's consider that the point that we're interested in is point O, point 0. Okay, so this is the point that we're interested in. And I want to determine the moment generated about point O. How much point O wants to rotate given some applied force F. So I've got some applied force F, okay, which I can represent by a vector. I think by now that we know that. And I'm also going to define some new vector R. I'm going to call R a position vector. Now, R is going to be measured from the point in question to the point at which the force is applied. And I propose that the moment can be defined as the cross product of R and F. So R cross F is going to be our formal definition of a moment. Okay. Now, like all vectors have a magnitude. I propose that the magnitude of that vector, and we're going to see a lot of this later, that the magnitude of that vector can be computed as the magnitude of this force F multiplied by this distance here. And this distance here is the distance from the point in question to what I'm calling the line of action of this force, the shortest distance. Okay? We have a name for that distance. We call it a moment arm. Okay? Right now, I'm sort of throwing a lot of definitions at you. We're going to spend a few lectures sort of digesting this and chewing on it. So we'll take our time with really sort of investigating what's going on here. Now, note again that the magnitude of the cross product is the area of the parallelogram formed by those two vectors. And we're going to see actually here in a second why this FD term works. And it actually all has to do with some really fundamental geometry. And that fundamental geometry also will help explain why the cross product is defined as R cross F, not F cross R. There is a very specific reason for that, which you're going to see here in a second. But does this idea kind of make sense? Yes, sir.
So why would D and R be different?
Sorry, say that again.
Why are D and R different?
That's a great question. The short answer is give me a little bit, and I'll explain why. But what you will find, what we're going to see later, is that R needs to be from the point in question to F. Okay. And I'm going to talk here in a little bit about the principle of transmissibility, but what I'm going to say is that R can actually point from here to here, 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 and you will get the same answer, okay? D is the magnitude of that distance, that shortest distance from the point to the line, whereas R is a vector, okay? So D is a scalar and R is a vector. But don't worry, we're going to digest this. We're going to take some time getting into this. I understand how that notation might be a little confusing now, but bear with me. We're gonna dig into it. All right. Everybody good so far? Okay. Don't worry. We'll take our time with it. Okay. Now, leading into this, I want to talk about something. This is actually mentioned in chapter 1 of your book, but I haven't really talked about it until now because it hasn't really been all that relevant until we started talking about the land of moments, and that's the principle of transmissibility. I think that a while back, we used the example of a tug of war to start explaining how we could add forces, right? And the idea was that if you have a bunch of forces that are all acting along the same line of action, in the same direction of that line of action, then all you have to do is add up their magnitudes, right? So in the case of this example, we've got 1, 2, 3, 4, 5, like 7 or so guys in blue, 7 or so guys in purple. And they're each applying various magnitudes of load to this rope, but they're applying them in the same direction. The only difference is one's, I guess, positive forces and one's negative forces because they're flipped along the line. So if I wanted to determine who was winning this tug of war, what I could do is I could take all the forces applied by the guys in blue, treat them as positive, all the forces applied by the guys in purple and treat them as negative, just add them up. If the answer is positive, the blue guys are winning. If the answer is purple, the answer is negative, the purple guys are winning. Okay? In the land of moments and in the land of rotation, what that means is that from a static standpoint, remember, we're treating vectors as sort of arrows in space, right? That there's a physical arrow in space. What that basically means is that from a static equilibrium standpoint, this force and this force really can be treated as statically equivalent. It's the same magnitude, same direction, same line of action. So I can take those values and I can actually move them along the line of action, and I achieve the same static equilibrium if I'm talking about forces. What that means is that we have a little bit of a better definition for R, and this is why R and D sort of co-align. Let's go back to our definition of the cross product. So remember, the cross product has to be, the magnitude of that result has to be the area of the parallelogram formed by the two vectors in question. Okay, so I have here a little animation that shows I've got a parallelogram and I've basically got a fixed base, but the angle is changing. Okay, but one of the things that's kind of interesting about this animation is that if you look, you can see how the parallelogram is shifting, how it's going from back and forth. But what if I told you that throughout the entirety of the animation, the area of the parallelogram remains unchanged? It does not change at all. Okay. So in terms of the relationship here, what I'm saying is that if you wanted an analogy, the base in this case sort of represents our force in question, right? So we have some point out in space, and there's a 20-pound force pointing this way. Now R, what I'm going to say is that R corresponds, here's a better way of defining this position vector. R starts at the point about which moments are taken, and it points to any vector on the line of action of F. So imagine this is our line of action, okay, and let's say here's our point. So R can go from here to here, here to here, here to here, here to here, here to here. And in the end, no matter which vector you use for R, as long as it starts at the point about which moments are taken and it ends on the line of action of the force, you will get the same moment. This is one of the reasons why moments are defined as R cross F and not the other way around. Now to go back to your question about the difference between R and D, I propose that in the end, R is any vector that points from the point the point in question to the line of action. Whereas D is just the shortest distance from the point to the line. So D in this instance would be the height from these two lines, and R would be the vector that points from the point to the line. Does that make sense? Is everybody else okay with that? Now to make that point and to sort of illustrate what's going on with the concept of moments, we're going to do an example, okay? Let me pull up the notebook. This example takes a little bit of explanation. So I want to sort of go through how we're going to do this. All right. So what we've got here is we have a rectangular plate, and it's being held up by, to be honest, a lot of the physical characteristics of the system don't really matter. But I have a plate, and it's being held up by some brackets. But what I really want you to focus on is this wire, okay? So I have a wire that has a tension inside it of 200 newtons. So imagine this table is the bracket, and I have a cable that's going like from this corner all the way up here. So I have a cable going from here, like all the way up here. That cable is keeping the bracket up. So it's yanking on this point with a force of 200 newtons. So I have a 200 newton force that's sort of going up like this, okay? What I want to do is I want to figure out how much moment that force is generating about one of the brackets, in this case, point A, okay? So what I'm going to need to do is I'm going to need to define this vector here, so this is the F vector, and I'm going to need to define a position vector. The position vector is going to go from the point in question, in this case A, to the line of action of this force. So the beauty of this is I could have a vector that goes from here to here, or I could have a vector that goes from here to here. Why here to here? Because this is the line of action of that force. So anytime that vector points along to that line of action of that force, I will get the same moment. And so the way to demonstrate that is I'm actually going to do this cross product twice. Okay? So we're going to do the cross product of this vector, and then we're going to do another cross product of this vector and that vector, and we will get the same answer, okay? Does that make sense? Now, it's going to take a little bit of work to get there, but we are going to get there, okay? All right, with me so far? Don't worry, we'll take our time with it. Okay, now I'm going to illustrate to you a little bit of a different way I'd like to go about starting to compute some of these vectors and whatnot. We're going to start to deal in some 3D land, and we're going to have a lot of 3D vectors that we're going to compute. So I'm going to show you a little bit of a different way of going about this, okay? So I want to look here at this image up top. We're going to call this the y-axis. We're calling this the x-axis. Calling that the z-axis. So this point right here is the origin, okay? Now the first thing I want to do is I'm going to look at this system, and we're going to define our distance vectors a little differently this time, okay? I've got this system, and I see 4 points labeled. I've got A, B, C, and D. The first thing I'm going to do this time is I'm going to see if I can determine the point coordinates. And we're going to call these in millimeters. So these are literally just X, Y, and Z points for each of these 4 points. I'll help you out. Let's start off with point A. So point A along the x-axis, that's going to be 0, along the y-axis, 0, and the z-axis, what do we got? 80, 240, so we'll call that 320. So is that 0, 0, 320? Does that make sense? Okay. What about point B? Can anybody tell me what the coordinates for point B are going to be? There we go. 0, 0, 80. What about point C? How about that? What's along the x-axis? Huh? 300. The y is still 0 because we're still on the plate. What about the z-axis? What is that? 80, 80, and 240. Was that 400? And finally, for point D, D is the only one that's going to have a y direction, or a y component. So it's x is 0, y is what? 240. What's z? What's that? 80? 80. Okay. All right. That makes sense? Okay. All right. So what we've got to do now is we've got to define, what's our formal definition of a moment? It's R cross F. So it stands to reason we need some R's and we need an F. So let's start off with the R's first. So I'm going to call those position vectors, okay? I'm going to try and link this new notation to what you're used to already. So let's start off with position vectors. And we're calling these R vectors. Okay? Now, I propose that for this problem, we are going to determine two position vectors. Okay? So we're going to determine a position vector that looks like this. And we're also going to determine this position vector. And I propose that if we cross either of them with the force vector, we will get the same answer. Because both of those vectors start at the same point and end on the line of action of that force. Okay? Now, how do we determine these? So let's start off with this vector here on the bottom. Now, up until we got to this point in the class, I think everybody would have called this vector AC, right? That's what you all would have called vector AC. Okay? Okay? Now, the textbook and the notation that we're going to start to use now is going to look like this. R, and it's going to say C/A. Okay? And what that vector basically means is that we are pointing to point C from point A. That's why the notation's like that. But if you're wondering, okay, why, Dr. Mike, you're making it more complicated. Why are you making the notation more complicated? Why do that? Here's why. Check this out. I propose what we can do is we can take the coordinates of point C, the coordinates of point A, subtract them, and therefore there's your position vector. Simple, straightforward way of getting those vectors. And check it out. So think about this. How do we go from point A to point C? How far do we go along the x-axis? 0.3 meters or 300 millimeters? How far along the y? We don't go up and down. And how far along the z? We go from here to here, which is 0.08. So it's a little bit more of a systematic way of determining those vectors. Does that make sense? Now, what I am going to do is, notice how I didn't write any units for this. So I want to make sure that I'm doing that. What are the units for that vector? millimeters. Okay, now we are going to need to determine another distance vector or position vector. So I'm going to do this vector AD. So vector AD I'm going to write as that, which points 2D from point A. And so all I'm going to do is take the coordinates of point D, take the coordinates of point A, and do some subtraction. So 0, 240, and then negative 240. And so our dA is 0I plus 240J minus 240K. I want to stop for a sec. I don't want to rush through that. Does that make sense? Is everybody okay with that? This new way of determining these vectors? Okay. So those are our position vectors. But now we need to determine a force vector. So how do we do that force vector? Okay. Well, we need a vector. So wait, this is a vector in 3D. How do we define force vectors in 3D? Seems to me what we would do is we would get a distance vector. Then we would turn it into a lambda unit vector, multiply it by the magnitude. Y'all remember that? So none of that changes. So we are going from C to D. All right? So let's go through that. So let's do our force vector. So the first thing we're going to do is compute CD. So that is, we take the D and the C and we subtract them. So D is 0, 240, and 80. And this is 300, 0, 400. All right, if it's okay, I'm going to scroll up a little bit. Do y'all have this up top? Okay, I'm going to scroll up a little bit because I'm sort of squinching this. Okay, so this is 0 minus 300 is what? Negative 300. This is 240. And this is negative 320. Did I do that right? Okay, so now we have CD, which is minus 300I plus 240J minus 320K. Now, what are the units for that? Millimeters, right? Okay. So in order to determine a force vector, what I need to do is I need to determine the magnitude of that vector. So I'm going to scroll down a little bit further. So I need to determine the magnitude of CD. And how do I determine the magnitude or the length of a vector? Pythagorean theorem. So I think we need to break out our Casio FX 115 ES Pluses or similar scientific calculators for this one. Here, we'll leave the units. What do we get when we plug that into our Casio FX 115 ES Pluses or similar scientific calculators? 500. Man, it's like I planned that or something. Do I have a second on that? Okay, good. All right, so now we determine our unit vector, and the way that we do that is we take the original vector and we divide it by its own magnitude. So we get oh, that's positive. Okay. I might be able to do a little bit of this mental math in my head. Let's see. So this is, actually, let's put it over here. So 300 over 500, that's 0.6. Plus 240 over 500, I think that's 0.48. And then negative 320 over 500, what is that? Is that 64?
Yep.
All right. What are the units for this vector? Make sure everybody's paying attention. There are none. It's unitless. I might start doing that a little bit here and there where I just write the vector with the numbers and then put the units over to the side so I don't have to keep writing the units over and over again. Okay. Finally, we need the force vector. Which is the magnitude times the unit vector. And what was the magnitude for this vector? What was the magnitude of that force? 200 newtons. So I might need a little bit of help on this. So what's, so 200 times 0.6, that's what, negative 120? Did I do that right? What about 200 times 0.48?
Positive 96.
Say it again.
Positive 96.
And then 64, was it 128? I did that right? And, oh, negative. See, this is why I asked for seconds. Okay? And the units for this vector are now in newtons. Okay, does that make sense? So let's just take a second and summarize the important stuff that we've done so far. Okay? Because ultimately, what we're going to compute are cross products, or R cross F. And what we've done is we've got two R vectors. We've got an R from C to A, which is 300I plus 0J plus 80K. We've got an R from D to A, which is 0I plus 240J minus 240K. We did those parts earlier, and then we just got this F vector right here. I want to take a second before we start doing these cross products. I just want to take a second and see, like, is this okay? Is this making sense? I mean, granted, while there's a little bit some new notation, I don't think what we're doing is all that different. I mean, we're just writing vectors, right? Just describing vectors. Sound good? Now, what I'm going to do is I'm going to do two cross products, and we're going to get the same answer for both of them. So let's check that out. So let's start off with the first one. Let's do R CA, and we're going to cross that with F. Now, you remember the way that we do that is we write a determinant. We fill up our first vector first, so 300, 0, 80, and then our second vector. Okay? And these are going to be big numbers, by the way. Just recognize that. And we'll talk about why here in a second, but these are going to be big numbers. All right? And so I'm going to use cofactor expansion. So we have I times a smaller determinant minus j times a smaller determinant plus k times a smaller determinant. And then the way that we get those determinants is we knock out the rows and columns. So if we knock out the rows and columns associated with I, we get 0, 96, 80, minus 128. For J, we get 300, minus 120, 80, minus 128. Yep. And then K, we get 300, negative 120, 0, 96. Okay. So what do we got? We've got I times what? What goes in here? So this times this minus this times this. What is that?
Minus 12,288.
We'll say it again.
Minus 12,288.
Hold on, you might want to check that because that's what I'm getting for something like over here. What about, so this one should just be 86 times 90. 7680. That's what I'm getting. Because it's this times this, which is 0, minus that times that. So it should be minus 7680. That makes sense? Everybody else get that? Okay. So this is minus j times what? Now this one takes a little bit of work because we got to do this times this minus this times this. So ignore this sign over here and just do inside the determinant. What do we get for that? Like, for example, this one, I think, is like negative 38,400.
28,800.
28,800 inside here. Is that positive or negative?
Negative.
Negative. Negative inside. Yeah. All right. Plus K times this. And that was just going to be 300 times 96. And 300 times 96, I can do that one. That one's also 28,800. So if I wanted to summarize that R cross F, I'd have negative 7680I plus 28,800J, you put a comma there if you want, plus 28,800K. Now, what are the units for that? One of the things we haven't discussed with moments is units. So what we usually do is we just say newtons times millimeters. So it's sort of like a torque, like a foot-pound or whatnot. So I could go on and on about, like, do we call them moments or do we call them torques? So that's another story for another day. So that's our vector, okay? Now, I want to show you what happens if we were to have crossed the other ones. What happens if we cross the second vector with F. Check this out. So if we do that, oh, sorry, wrong one. What I got to do is I got to use the second vector, but the same force. And so watch what happens. So I fill it out. So follow the same pattern, just new values because it's a different formula. Or different, same formula, different position vector. So what happens if we do this first one? What do we get inside here? Negative 7680. Do I have a second on that? Ooh. What do we get for this one? It's almost like we get a... Wait, do I have a sign wrong? Yep, I do. I have a sign wrong. That's supposed to be positive. So I get negative 240 times 120. It's almost like that's 28,800. What about the third one? I get 28,800. It's almost like R dA cross F equals 7680. It's almost like they're the same. I mean, look at that. Look at that. And look at that. Again, as long as your position vector goes from the point in question to the line of action of that force, you will yield the same cross product. So just so everybody's aware, and then we're going to call it, just so everybody's aware, the answer, we're trying to determine the moment about point A is this vector. So negative 7680 I plus 28,800 J plus 28,800 K. That's your answer. And yeah, that's a vector, so I need an arrow over that, and that's in Newton millimeters. And again, because we're taking newtons and we're multiplying by millimeters, and millimeters are so small, hence why the answer is so big. So that's the answer, okay? Does that make sense? All right, I'm gonna pull up the QR code. We got a homework due Monday. I'll keep working on the exams. That's all I got. Y'all have a wonderful weekend. Hold on. Oh, let me put the answer here.
I'll text you.